Okay, our next type of symmetry, which is our third and final symmetry, is called point symmetry. So far we've learned two different types of symmetry. So far we have learned line symmetry, and we saw what that looks like. It's a line that is basically the line of reflection that maps a point on an image to the image itself. And we also learned rotational symmetry, and the last thing we're going to learn is called point symmetry. So what is point symmetry? Let's take a look. So a figure with 180-degree rotational symmetry also has point symmetry. Each segment joining a point and its 180-degree rotation image passes through the center of rotation. So what does this mean? Well, we took a look at things that had rotational symmetry. For example, this regular pentagon has rotational symmetry. In other words, it can rotate 72 degrees and the pentagon will map onto itself. It also has an order of 5, which means the number of times that I need to rotate when the figure maps onto itself is 5. In other words, A goes from here to this point, to this point, to this point, to this point, and then back to itself. So that has an order of 5. What we're saying here is that a figure with 180-degree rotational symmetry also has point symmetry. So let's find something that has 180-degree rotational symmetry. Let's see. So let's take a look at these two polygons. Which one of these has 180-degree rotational symmetry? Well, let's take a look first at this regular hexagon. So I can rotate this 180 degrees. Okay, and you can see that this figure will map directly onto itself. In other words, every point when rotated 180 degrees will map onto the regular hexagon. Let's take a look at the regular pentagon. In other words, does a pentagon have rotational symmetry? If I rotated this point over here 180 degrees, will it map onto the regular pentagon? Let's see. Let's try to do this again. And so let's try this again. Okay, so here is the pentagon. I'm going to rotate this 180 degrees, and does it map onto the regular pentagon? Well, no, it doesn't look like it does. Right? So a regular pentagon does not have rotational symmetry, because if I rotated this 180 degrees, here it is the regular pentagon, the one I started with, and then when I rotated 180 degrees, so what I want to do is, let's focus on, let's see if I can, so there is my original figure. And what I'm going to do is, let's take this and there's my original figure. I'm going to rotate this 180 degrees like this, and as you can tell, it does not map onto the original polygon, the original regular pentagon. So a regular pentagon does not have point symmetry, whereas a regular hexagon does have point symmetry. Let's take another example of point symmetry. So it says point symmetry is when every part has a matching part. That's the simple explanation. Basically what it says is that if I took a look at any point on this figure in quadrant 1 and I reflected it over this point over here, you would map onto a given point like that. If I took this point over here and I reflected it over this point, it would map onto this figure right over there. If I took this end point of my curly Q and I reflected it over this point, this point of origin, it would map onto this point on the curly Q. So the same distance from the central point is what each of these matching points are. In other words, each of these points are the same distance from the origin, but in the opposite direction. So it's the same as rotational symmetry of order 2. As you can tell, if I took this entire figure and I rotated it 180 degrees, it would map onto this figure here. and then if I rotated it again 180 degrees in this direction, it would map right back onto itself, so it has rotational symmetry of order 2. Here's the important part. Point symmetry is sometimes called origin symmetry. Why? Because the origin is the central point about which the shape is symmetrical. In other words, this shape is symmetrical about the origin. So basically what we're doing is we are rotating it around this point of origin. We are also reflecting it around the origin. So those two things must be true. Those two things must apply. Let's take another example. So playing cards often have point symmetry so that they look the same from the top or bottom. What we're saying is this is, for all intents and purposes, your point of origin. And every point, for example, the bottom part of this heart, when reflected over this point of origin, let's make this another color. There we go. When I take any point on the top part of this card reflected over this point of origin, will map to another point on this figure. If you take the hilt of the king's sword and you reflect it over this point, you get the hilt of the king's sword. If you take the K over here on the lower right hand corner and you reflected it over this point of origin, you would get this K over here. Each of these letters also has point symmetry. In other words, every point on the right side of this N, so this point right over here on the right side of this N, if I reflected it across this point of origin, it would map to a point on the N. If I took this point over here on the N and I reflected it over this point of origin, it would map onto this point on the N. Let's take another example. So it says, which letter has point symmetry? So A certainly does not have point symmetry. If I took a point on A, there's no central point, there's no point of origin that I can reflect it over to map back onto A. There might be one point that reflects over a point of origin directly onto A, but not every point. So which one does? So this one does not. This letter certainly does not the A. The B certainly does not. In other words, if I took the letter B, right, and if you decide that you want the central point to be here, right, this point on B, if I reflected it across here, would be outside the B. This point over here, that might reflect onto the B over here, but this point of the B, when reflected over this point, would be somewhere over here, so that does not. W also does not have point symmetry. However, if you take a look at the letter H, every point on H could be reflected over this point of origin, so to speak, the yellow dot, and it would map onto a point on the H. Also, the way you can look at it is as follows. If I can take this figure, and I can rotate it around that point of origin, that yellow point, if I rotate it around 180 degrees, it would map directly onto the other part of the left side of the letter H. You cannot say that about any one of these other letters, either A, B, or W. So what kind of symmetry does a circle have? Does it have line, rotational, or point symmetry? Well, you might have guessed it. It has all three. I can draw an infinite number of lines that would map one point on my circle to any other point on my circle. It also has rotational symmetry because I can certainly rotate this around as many or as few degrees as possible and they would map onto the circle. And it also has point symmetry. In other words, I can rotate this 180 degrees and I map onto the circle. So it has all three. Let's take a look at this. Here's another description of point symmetry. A figure has point symmetry if there is a central point so that the part of the figure on one side of the central point is the reflection of the part on the other side. Remember how I said that think of point symmetry as a point of reflection or a midpoint between any 2 points on the figure. So for example, if you took a look at this point right over here, notice how you can take any point that is on the letter S, you can reflect it over this yellow point and you'll get another point on the letter S. if I took this point on the letter S and I reflected over the yellow point, I would get to this point on the letter S, and so forth for every other point. Let's take a point on the letter N. Okay, so if I call this my midpoint, any point that is on the letter N, when reflected over this yellow midpoint, will map onto another point on the letter N. If I took this point on the letter N and I reflected it over the yellow midpoint, it would map onto the letter N as well. And think of it as two lines that intersect at a midpoint. Every point on this side of line PC prime will reflect over line P and will map onto PC. Same thing with AP. Any point on the line AP, when reflected over point P, will map onto PA prime. And the same thing over here. Here's just another example. So if you have, for example, this is your midpoint, any point that is on this figure, when reflected over this midpoint, will map onto the figure itself. And there you have it. That is the essence of point symmetry.